we are talking about shadowing in Opengl. So there are kind of scenarios where, like if we depth test in Opengl, like if I have a okay, so this is eye or camera, one surface, another surface. Okay, so this surface would not come into the picture. Okay, so that is the scenario. Otherwise, if we don't enable depth testing, then whatever we draw next, it will come into the picture because it is going to the color buffer. So there are kind of three. Frame buffer is another data structure that carry color buffer, depth buffer, stencil buffer. And if we don't enable depth testing, then whatever we do in kind of drawing, everything go in color buffer. So that is the scenario in depth testing. So the kind of the surface that is obscure or that is behind, those would not come into the picture even though they draw afterwards. So that is depth testing. Now what is shadowing? Okay, so this is eye. Here is one light, and here is one kind of we can say one model. Now if light falls, the model that is behind the light, that should not be shown, even though from the eye it is visible. So now there is another guy came shadowing. So one model, one item is obscuring other item. So it is kind of doing a screen effect, and other would not be shown. So how we can kind of achieve that kind of effect? Like if we see in the real world, then if we see lunar eclipse, then it comes behind the scene. So sunlight falls on earth, and that is full moon night. Okay, somehow generally full moon night, if it is sun, earth, then moon will be kind of exactly behind the scene in the east side when sunset happens, but it will be at an angle that earth will be not in between. So that is full moon night. But if earth comes in between, then the light would not fall on the moon, means it will come in a kind of a shadow, it will come behind the scene. So then that cannot be shown. So shadowing, how we can achieve a shadowing in Opengl? So shadowing is similar to depth map. Okay, so if I have an eye camera that maintains depth, then I have a light that will also maintain depth. So the pixels that are in front of light, they will be lit, they will glow, and behind the scene, they won't let glow. So at the end, whatever the depth map, the depth hashing or mapping, whatever we achieve from the light, and what is the actual through the eye, through the camera, the latter will mix up, will merge. So one hint we are giving to the camera that these places, that these pixels would not be shown, even though they are in front of the camera, but they are coming kind of behind some object if I see from a light perspective. So that we'll see in the discussion that how we can kind of use it like a texture. Texture is nothing but it's a kind of mapping one. So it has texture has a set of pixels, texture. So set of texture we have. So each set of texture we can kind of keep information that so if we see at the end in the frame buffer, everything comes in a set of pixel only. So whatever we see in frame, so it is depth or not depth, it is stencil or color, whatever, it comes in a set of pixel only. So if someone is seeing from the light perspective, then it is like a frame buffer and what he sees. So each pixel would carry the depth information. If a particular kind of a pixel that is in front of the light, then how much depth it contains. So it will contain another texture. Depth map contain from the eye, it contains another text, another mapping. So whatever mapping we receive from the light sources, so we will rotate the projection and model view in the sense that light source become eye, and then it sees. Like we have already seen the depth testing. That camera is the eye, and then it sees which is where. So when we say I want to place model at this coordinate, this coordinate, this coordinate, that coordinate, then it thinks that which all are going to be screened. So that way we will rotate the projection and model view in a sense that light will be light source. The light source will be camera, and then it will kind of it will see from this 2 points. One is the actual camera. Now light is becoming the camera, and we rotate the projection model view. Now we know that in this fashion that which model is at which depth, and then we create a kind of, we'll have a texture, and there we'll fill that these are pixels that should be visible, and these are at what depth, because we know that models are at what depth from the camera's perspective. Now this information, now we'll pass it to the camera, whatever we have received from the light, that these pixels are kind of going behind the scene, so that it will take care, and then they would not come. Later we can display the shadow also as per the texture. So we'll see the kind of not very complex, we know kind of projection and model view and how they change when we place models here and there in the various z coordinate. Then both are z coordinate, either I see from the light or I see from the actual camera. So that we'll see. Okay, so further to discussion on shadowing. So we'll proceed on Linux Mint. Okay, so we'll cover the topics. Okay, so we'll cover shadowing in Opengl and camera and the light model, and frame buffer architecture, depth buffer, texture map, shadow acne, and how shadow acne is kind of that we can remove, and adding bias. So this is one of the solution for the shadow acne. So that we'll see. Okay, so this is camera that is placed at origin, and this is light source. It is placed at some hypothetical point XYZ. So if light falls on a surface, then on the another surface it makes a shadow. So this surface has a color yellowish, and then there is a shadow. Shadow is because of this spherical surface, and it is because there is a light source here. Okay, so there is a camera that is placed at the origin. So in Opengl analogy, we can kind of think light as a camera only. So from camera, photograph is being taken, and this portion cannot come on any another surface. If this portion cannot come, then this is a shadow. Okay, and So this is kind of a light analogy. And a fixed camera that is placed at the origin, and if this surface, another surface is getting obscured by this surface, then this surface cannot be drawn, that portion cannot be drawn. So that is the difference between camera and light. So both are kind of, they look into the scene. When camera look into the scene from the origin, then the surfaces that is obscured, they do not pass the depth test and they do not come. Whereas when it is light, then when we draw the surfaces and if any region is getting obscured, that is drawn as shadow. Okay, so how kind of we can achieve this effect? Like how we can achieve the effect of shadow? So that we will see. Okay, so if this is camera and this is light, if I see from the light perspective, then it would look like this. Okay, so if I see from the light perspective, from the light source, it should look like this. And where the actual thing is, that is the sphere where the light is falling. So underneath there is shadow. So we are talking about how light sees. If camera is placed at the light location and then it look in this direction, then it sees a sphere and then it is followed by a kind of another surface that is a plane. So if camera is placed at the light source, then it would see exactly like this. Okay, and where this shadow portion is obscured by this sphere. Okay, so we'll proceed. Okay, so Opengl is nothing but it's a kind of mathematics. There is nothing light and a ray of light, and there is no physics here. Okay, so Opengl, there is no physics, there is no chemistry, there is no biology. So it's a pure mathematics. So I mean kind of set of vertices and matrices, and then matrix addition, multiplication. Okay, now can we think light? So light is here. Can I place light here? Light is at x, y, z, and how I look from the light perspective. If I look from the light perspective, it would see like this. But this is not a sentiments, right? Means it's a pure mathematics. So how we can kind of solve this? How a light, if camera is placed here, and when it sees the sphere and when it sees the surface, then it would see like this. How it would happen? So we can think like the light source is placed at the camera location. If light source is placed at camera location, so this is camera, then white is light source, then it would see exactly like this. So light source, okay, now we can think like light source from here, it got rotated, transformed, and it came here. Or from here, we do some rotation transformation and we bring the light here. Okay, what I am trying to say is how I can think that from light it would see like this. So one solution is I have to bring light at the origin. If I bring the light at origin, then it would, if you see in z direction, then it would see like this. How I can bring light from xyz, that is the hypothetical distance, to the origin? If that is the idea, then we have to push some rotation and translation into the model view matrix, and light would come here. If light comes here, then it would see the image like this. Okay, so now we talked about a series of rotation and translation that need to be done on the light source, so that light source come at the origin. Okay, so if this is true, okay, so further we'll take it. Now, if light source is here and it can see the two surfaces like this, and if I rotate the light source along the y direction, then this surface would become like this. Okay, so the surface would become like this. So if light source is consistent here and I rotate the axis y along the y axis, then these two surfaces would become like this. Okay, now so that I can say kind of a GL rotate. So GL rotate along y axis when the light source is placed at the camera, then whatever we are seeing, the two surfaces, so two surfaces would turn like this. Okay, so means this is how it changes. So rather than, means I gave one example like how rotation and translation happen. So a simple case is if I rotate along y axis, then this diagram would become like this. Okay, now rather than I do rotation and translation series of, so that this light source would finally come here, the light source from the origin, it would come here and it would start looking like this. We can use a ready-made kind of utility from the GLU, that is GLU look at. If I use this, then GLU look at takes care of transforming the light source from origin to this position. Okay, and then when it comes to from origin at this position, certainly it does changes in the model view matrix, and then it can look like this. It will give kind of a similar impression where the light source is placed at the origin and looking in the negative z direction. So we'll use GLU look at. So GLU look at, if you see the grammar, then GLU look at first talks about kind of where the light is placed, in what direction it is viewing, and then what is its kind of up direction. Okay, so this light source, it can be up in the y direction, it can be up in the x direction or in z direction, it can be placed at xyz, and where it is looking at. So I can say that it is not looking at the sphere, it is looking at the origin. Okay, so this light source is looking at the origin and light source is placed at xyz. So it's a kind of a camera analogy and it's up vector. So that is in y direction. So if I do that way, then now it is responsibility of GLU look at to do these rotation and translation. Rather than we do the rotation and translation in the light source. Okay, so we can also do rotation and translation of the light source so that light source would appear here, and then how it would see the surfaces, then it would see the surfaces like this. Okay, so rather than we doing the rotation and translation, GLU look at does the rotation and translation. We have to provide some input and then we get series of rotation and translation. Okay, the final aim is that we have to look from the origin perspective. Why? Why we cannot look from this perspective? That is the question. So why I cannot look from here? Why I have to come and look from the origin? Okay, so that I can view the two surfaces like this. Why I can't see the two surfaces from here only, from the x, y, z? Why I can't do these two surfaces like this? Okay, why I need to do kind of so many transformation and bring the light source at the origin? Okay, so we'll understand little more now. So in Opengl, everything is placed at the center. Okay, so Opengl starts with a concept where everything is placed at the origin. Model and camera. Camera means view. So camera and the model both are placed at the origin, at the beginning. Now, these models or surfaces, one surface, another surface. Now they got transformed and rotation and they are into the scene now. Mr. Camera is also got translated and rotation and it came here. Okay, I think we can see kind of in little minute way. So camera, so this is violet color, this is the camera, and this I believe yellowish color. So this is model. So camera from the origin, it came here. This is what we are doing. Means the light source from the origin, light source was kept at the origin at the beginning and light source came here. Same way models, they also, so there was rotation and translation in the camera or light source, it came here, and model also it passed through rotation and translation and it came here. Now if I manage this camera through one matrix and if I manage this model through another matrix, then there are two matrices. One is called view matrix, one is called model matrix. Okay, I think it's a good idea to see our tutorial, video tutorial on kind of these transformations and model view matrices. Okay, so now we have to maintain camera matrix, that is the view matrix, and this surfaces matrix, that is model matrix. Should we do this? That is a big question. I mean, if we see the actual mathematics, if we go for one more variable, complexity means I have one variable, a equal to 10 and a equal to this, a equal to that. If I introduce one more variable b, okay, then complexity grows in GP, geometrical progression, not in AP. Okay, I think it's AP. And it grows in GP. So it's not a kind of fashion to introduce variables. If we introduce variable, then very quickly it will go out of human brain. Okay, and at the end program never executes on computer. Okay, so this is a false belief that at the end computer has to execute the program. We can introduce variable as many as we want because it makes our life easy and let the computer do its work. So I think it's a worthless statement. So everything gets executed in the programmer's mind only. So If programmer cannot execute the stuff in his own mind, okay, then computer cannot also execute. So computer is less powerful than human. I mean, this is how a programmer should think. So if it is going out of the kind of control of a programmer, if I keep on introducing variables, then tomorrow if computer runs very nice, then output is coming very nice, then there is no problem. But if output is not very nice, then programmer won't be able to debug it. He cannot modify it, because anyway it is out of his mind. Okay, so it's not a fashion that we introduce matrix and matrix. So can we club camera or view and model in one matrix? Okay, so now the idea is that can we keep the camera static at the origin? Camera is static at the origin. Camera cannot move. Whatever we want, we have to achieve everything through the transformation in the model only. So what we are seeing here, when camera is viewing from here, at the end, this whatever we are seeing, this is the Z direction of the camera. If this is the Z direction of the camera and camera is viewing like this, then why not we place the camera at the origin only and let model move like this? Now can we change the model matrix and view matrix to one matrix called model view matrix? In model view matrix architecture, view cannot change. View means camera. Camera always static at the origin only. Whatever you want to achieve, you have to do the transformation only in the model. Okay, so model can do any kind of acrobatic action in front of the camera. Camera cannot move. So we'll stick to that solution. Camera cannot move. So if I consider light at the beginning only, if I consider light as camera, then we are moving the camera. That is not the idea. Okay, there are two camera now. One camera through which we are actually seeing the picture, and light is also behaving like a camera. If light is behaving like a camera, camera cannot move. Okay, if light is here, then light is anyway, it is seeing the model like this. If it is seeing the model like this, then we'll place the light also at the origin. If I place the light also at the origin, okay, then to get that similar effect, we have to do some rotation and translation into the model so that it would appear like this. For time being, from the light, if I consider camera is here, then for the time being, we have to do translation and rotation in the model itself. That is this translation and rotation. That is GLU lookat. So GLU lookat make us believe that light is placed at the origin. If light is placed at the origin, then what translation and rotation we have to do in the model so that it should look the same way as, okay, so if light is here and whatever light is seeing the model, if light is placed at the origin as a fixed and whatever it is seeing, if that I have to kind of emulate, simulate, then what is the rotation and translation I have to do in the model? That will achieve through GLU lookat. It's a ready-made kind of API, and it is not part of Opengl. It is part of Opengl, I think, utility. It's not GLUT. It's not Opengl utility toolkit, but it is Opengl utility. So that we will use so that we can happily place the light here, transform, then rotate the light here so that I can see everything in the -z direction. Okay, so that is the concept. Now it is kind of we have the kind of the control in our hand now, because we are born and brought up in a way that camera cannot move. If camera cannot move, then everything has to be moved in the model only. If that is the concept, we maintain only one model view matrix. If that is the concept, and if I consider light as a camera, then light I have to bring at the origin. If I have to bring the light at the origin, then how much transformation I have to do in the model, so that the model should look like this, the way it should have been looked from the light source. So that we will achieve through GLU lookat. Okay, so fine, so good. So as at the beginning I kind of discussed that shadowing is not a difficult task. Shadowing is a matter of research, and it's a matter of research because it's very intricate. If we miss a single point in shadowing, then we would pray that there should not be any shadowing. Okay, it's very intricate. Someone has to understand full concept of matrices, transformation, then texture, then texturing, then depth, then various testing, and then camera analogy, then pixel densities, then resolution of your screen, then viewport, then projection matrix, then model view, every minute detail, all the matrices, model matrix, view matrix, projection matrix, how matrices they change when we go for translation and rotation, what GLU look at, how it modifies the matrix, everything. If you miss one point, then shadowing is out of your control. Okay, so in kind of general convention, people call it's a matter of research. Okay, so that is how it is matter of research. Okay, now how we can, so now we understood that why we use GLU lookat and why we want to place light at the center, because this is how we are brought up in Opengl, that view must be at the center. There should not be two matrices, there should be only one matrix, that is the model matrix, and we call it model view matrix. Okay, now, so if light is placed at the center, origin, then it sees the model like this. Can we think whatever the light is seeing as a raster value? Okay, so this is a raster value which is filled with 1, and whatever object it is seeing, the distance from in the z direction. Okay, so this model is placed in the z direction. This is x direction. This is y direction. And depth wise, this is z direction. So in z direction, if I look from the camera light, then everything is filled with a value called 1. That is the white that I am showing. Okay. Now when it sees the plane, that is yellowish plane, that is at distance of 0.7. Okay. So this will be decided by projection matrix. So when projection matrix we specify like GL ortho or GLU perspective, I think better we talk about GL ortho, then we give the near and far plane. So if I see the near and far plane, the far plane is 1. If far plane is 1, then what is the ratio from the near and far? So if I give near and far 1 and 100, and this guy is placed at 70, then this is a candidate of 0.7. And this blue sphere, it is placed at 40, then this is a candidate of 0.4. This is how it would it will create a kind of raster data structure. Can we think like this? So from the light source that is placed at the origin, looking at the minus z direction, then everything what comes into its scene, that is white, means that is 1. And then wherever the model is placed, that value will place in the respect to the 1. So if I say that kind of okay. Thank you. Okay, so if we talk about a projection matrix, then projection matrix is nothing but from one point. So from one point a person is seeing in minus z direction. So if he is seeing in minus z direction, so there is a near plane and there is a far plane. So it make a cube. I don't think I should be able to draw it. I hope so. There will be a cuboid. I think that's enough. So there is a cuboid and inside the cuboid models are placed. So this is near and this is far. If far is 100, and I want to fill this raster data, then this yellowish color is at 70 and Mr. Sphere is at 40. This is what I want to say. Now, if that is the case, then our kind of raster data can be filled like this. So 0.4, 0.4. So sphere is at the center. If I have like this, so what we are trying to say, if this light source is there, I bring it to the origin and then whatever we are seeing, it becomes like this. Then we fill a raster data and depending upon the distance from the camera, so one is maximum distance where there is no object and then 0.7 and 0.4. It would fill like this. We'll proceed. Now there is an arbitrary red point. Can we see the red spot? So there is an arbitrary red spot. Now this red spot is seen from the camera and red spot is seen from the light. From the light, now red spot is a candidate for shadow. Can we see? Actually, red spot cannot be drawn. Red spot can be seen from the camera, but red spot cannot seen from the other camera, that is the light source. So if it is seen from the camera, then it should be shown. But if it cannot be seen from the light, then it should be shadow. If it cannot be seen from the camera, then it should not be shown at all. But it can be seen from the camera, it cannot be seen from the light source. It should be shadow. How we calculate the shadow? Now, for any vertex, that can be seen from the camera, it's fine. Means it's a candidate to be shown. Now, we will do the translation of the light source and rotation, and we bring the light source here. And then light source sees like this. If it sees like this, then it cannot draw it. If it cannot draw it, but drawing happens not from the light perspective, drawing is happening from this camera perspective. There are two cameras. Then it should come as shadow. So I am going to compare from here. So red spot, so red spot distance, if I see the red spot distance from the light source, if this is 0.4, then this is 0.7. Now, can I talk more now? So, if this is the camera and I am talking about this pixel, this pixel should be drawn or not? It should be drawn because it is in front of the camera. What should be the value of the pixel? Now camera raised its hand. Camera just can say that I can view it, but I don't know, means it looks red, but I don't know what color it should receive. Now this went to responsibility of the another camera, that is the light. Now light is transformed, rotated, and it came here, and then he is seeing like this. Now where the red spot is, okay, where the red spot is, red spot is somewhere here, that is obscured by this sphere. So red spot cannot be shown. So camera number 2, that is the light. Camera number 1, that is the primary camera. I can say my eye, the eye of the viewer. He is saying I can see this red spot. I want to see this. I want to draw this pixel. Now light source is it is referred, and light source is transformed to the camera for some time. I mean temporarily, and then it is looking at its raster data, and then it is finding the red spot somewhere here, and red spot distance is 0.7, where 0.4 is already filled. So camera can say that your red spot, what you are showing me, I mean the light which is placed at the origin now, it would say the red spot that what you are showing to me, I cannot see. So two cameras. Camera 1 is trying to draw the pixel, and then camera 2, that is the light that we brought temporarily to the origin, and then we saw in the Z direction, and then it is saying I cannot see. If it cannot see, then we collect those pixels which light source cannot see, those should be drawn as shadow. So two camera. One camera is saying, like I think we saw in one diagram, where there is a surface which light can see. There is a surface which light can see, but this surface cannot be seen by camera. So this camera is the boss. This camera is secondary. Light camera is secondary. This boss is saying that I cannot see this model. If it cannot see this model, then it is gone. There is no question of shadow or light. Okay? But if a pixel is in front of the primary camera, then it will say that it's a candidate for me. I am going to draw it. Then it refers the another camera, that is the light source. Temporarily we bring the camera at the origin. Through GL you look at, and then we say, sorry sir, I cannot see. So in that case, we come to a conclusion that pixel color would be shadow color. I mean, I can select the shadow color. This is shadowing in Opengl. Okay. So what we see from the primary camera, so that should be visible, and then we go for the light camera. Through GL you look at, through series of rotation and transformation, we bring at the origin, and then we refer, since we have created a hypothetical raster and we filled it with the data, so then that red spot we refer and we say that, sorry, it's not visible, and then it becomes a candidate for the shadow. Okay, so what a camera, so we can do kind of a transformation of this raster into actual image. So white color is 1, then 0.7 is little shadow, little dark, and 0.4 is dark. Okay, so we are done. Means this is shadowing concept. So whatever we are talking about, this hypothetical raster data, hypothetical two-dimensional array, who is going to maintain this? Who is going to kind of draw it? Okay, so we'll come to kind of frame buffer concept. So frame buffer concept, is happening behind the scene that we don't see. So when we bring Opengl stuff, then frame buffer concept happens that we don't see. So by default, we get a frame buffer. What is a frame buffer? Frame buffer is a data structure. Frame buffer is not a buffer at all. Okay. So frame buffer is a data structure. And this data structure has actual buffers. A buffers means a kind of multi-dimensional array, single dimensional array, where the kind of memory lies. So depth buffer, color buffer, stencil buffer, accumulation buffer. So we consider frame buffer as a structure, C structure, and it has fields: depth buffer, color buffer, stencil buffer, accumulation buffer. Depth buffer is not a buffer at all. So it's a kind of just a container of buffers. So depth buffer, color buffer, stencil buffer, accumulation buffer. Whatever we are trying to do is a candidate of depth buffer. Okay, because we are seeing in the Z direction, we are trying to draw the depth. So it's a candidate of depth buffer. Now, so by default we get one frame buffer. In that frame buffer, we have depth buffer, color. Whatever we are seeing on the screen, that is the color buffer. Okay. What we don't see on the screen, that is depth buffer, stencil buffer. So these are kind of intermediate buffers, and they are referred so that a final pixel will go in the color buffer or not. Okay. What is final pixel? What is the initial pixel? What is primary pixel? So that we will see. So our monitor is connected to the color buffer. Okay. Behind the scene, these buffers are there. So mathematics will happen on these buffer, and if it passes through, then it will be copied to the color buffer. Now we are not interested in color buffer, stencil or accumulation buffer. We are interested in depth buffer because we want this raster data. That is possible only through depth buffer. Okay. Now we'll talk about more grammar. So I have a kind of a surface. So this is a surface. Surface goes through some kind of transformation. So there are three vertices. One vertex, another vertex, and there is a third vertex. There are three vertices. If there are three vertices and it's kind of a primitive with GL triangles, then it is a triangle. If it is a triangle, okay, now we can do transformation on the vertices. Opengl is a game of vertices. Opengl is not a game of edges and surfaces and this and that. Okay, Opengl is a game of vertices. Like electronics is a game of resistance. So Opengl is a game of vertices. So we can do transformation on the vertices. One transformation is done, then we can draw the triangle again. Triangle is not getting transformed. Vertices are getting transformed. So after doing the transformation, okay, now we receive a new set of vertices. Now we can estimate the surface. So this is kind of, we can say that this is transformation. Okay, so transformation happens generally in the vertex shader. Now we are ready with the final transformation. Then it comes what would be the pixel inside it. So it depends upon what is the pixel density of our screen. So those many pixels will be contained inside the surface. If there are pixels, then there will be color. This is fragmentation. Okay, fragmentation is when there are two shaders. One is geometry shader. How vertices are transformed to resultant vertex. Now once vertex is ready, one surface is ready, then how all the pixels inside the surfaces will be colored. So that is fragment shader. It is not pixel shader. It is fragment shader. For each pixel we have colors: red, yellow, blue, green, and so and so. Okay, so our geometry shader, our vertex shader or vertex shader does geometry, bring the new geometry. Okay, then fragment shader, whatever the pixel, that is rasterization it is called, whatever the pixel estimates are inside this, those are getting colored. Once they are colored, now they should be shown on the screen, but they cannot be shown on the screen because like this is one surface that is triangular. Like this, there are many surfaces. One surface is above another surface. Then that surface is above another surface. Like this so nice triangle is, but it is behind one rectangle. If that is the case, few pixels cannot be shown. So in the color buffer, we cannot copy it as it is. Because if I copy it as it is in the color buffer, then triangle has to be shown, but it cannot be shown. So now we will talk about the Z value, the depth value of each pixel, and it will go in the depth buffer. So from the fragmentation is nothing but the each pixel color. Each pixel color has a depth value and it will go in the depth buffer if we have enabled the depth buffer, followed by stencil buffer, accumulation buffer. Okay, a stencil buffer is a kind of one stencil we place and we see if it passes the stencil. Like that accumulation buffer, we have series of images. Okay, whatsoever. So we are talking about depth buffer. So if it passes the depth buffer, then only it is not passing the depth buffer. Okay, some reason is getting obscured in the depth buffer. Okay, like this is the beginning what we saw. Okay, so this is a yellow surface. It is a yellow sphere, but it is not passing the depth test at all. So it cannot be drawn. Even though fragmentation is happening and there is a yellow color. Okay, if that is the case, then depth buffer would not pass certain part of the fragmentation pixel and it will be obscured because this rectangle has less Z value. This is kind of analogy of frame buffer. Then it comes to color buffer. Frame buffer dot color buffer. I am saying frame buffer dot depth buffer, stencil buffer, accumulation. So whatever is the resultant of the fragmentation, so I think I can name it. Okay, so thank you. So this is the, so I can write here. Okay, so this stage we achieve. So this stage is transformation. And this is achieved in vertex shader. Whereas this stage is called rasterization. Once transformation is finalized, then this process is rasterization that happens. Okay, it doesn't happen in any kind of shader. So this is rasterization. Once rasterization is done, then each pixel should receive a color. So rather than we saying a pixel receiving a color, we say that each pixel is receiving a fragment. So now pixel is termed as fragment. We don't call it pixel because it is not going to the color buffer. If it goes to the color buffer, we name it a pixel. So this is fragment shader. Okay, where each pixel after rasterization it is receiving the color, but it will not go to the depth color buffer if it is not passing the depth buffer. Okay, so like we saw. Okay, so I can save it. Like we saw, fragmentation happened for this surface and yellow color was assigned, pixel value, everything was done, but it didn't come to color buffer because it was kind of rejected by the depth buffer. Okay, now we are ready. So can we maintain? The idea is how we can maintain this raster data. We can maintain this raster data in an image. So we can have a kind of a separate frame buffer data structure. Anyway, we have frame buffer data structure in Opengl. We can instantiate it. And after doing the instantiation, we have depth buffer, color buffer, stencil buffer, accumulation buffer. Okay. So we will just keep the depth buffer and we will mute the color buffer. We don't want color buffer because we are interested only in the depth. Okay, because we want this raster data. This raster data, either we do all the mathematics or we find some kind of feasibility that is already available. So if I have a camera that is, light camera that is placed at the origin, okay, then I have a projection matrix, I have a model view matrix, then I can draw it. If I can draw it, then I can draw it on an image, all the texel of the image would contain this value. So far or 1, and then all the depth will have this value. It's possible that will show. So if I disable color buffering, enable only depth buffering, and then I try to draw this diagram showing some projection and model view matrix and map this to a texture will have this value. Because this is what we are drawing, and this value we need it. Okay, once I receive this, then this calculation is possible, what we showed. So we are using ready-made fundamental of frame buffer concept. So we have one frame buffer that we are seeing. We will instantiate depth frame buffer. We will mute color buffer. We will let depth buffer move ahead, and then we will place our light as a camera at the origin and will take the picture in the frame buffer, and that picture will save in a texture where each texel will have this float value. Then we get the raster data. Okay, we'll draw the raster data, what we receive in the texture, and it should be like this. Okay, one raster data is okay. So one raster data is ready, which is the texture. Then we are ready. So once light is here, then it would see blue color sphere, yellow color kind of plane, but there is another sphere that is red color that is behind the scene. So that would not appear as a depth test, since it is not appearing as a depth test inside the new frame buffer. So one frame buffer, so there are two frame buffers. Okay, one frame buffer is maintained by this camera, that anyway we have one frame buffer we will instantiate, and that is solely for new camera, that is the light camera. So in light camera frame buffer, we are seeing the projection matrix, model view matrix, we are seeing the image like this. We are placing the image in a texture and will use its texel as distances, and then we will use as a reference when we draw the final. So when we draw the final from the camera, that is called final pass. Two passes. One pass will generate the depth, and final pass, that is from the camera, actual camera, when we draw any pixel. So from the actual camera, this is the final pass. One pass is light is placed at the origin and we take a picture, and this picture is a frame buffer, new frame buffer, we save in a texture and we have texture data. And in the second pass, that is the camera, the actual camera. Now for any pixel what we are seeing, this pixel we will refer in the texture map that is taken from the light perspective, and we will see this pixel's depth value. Okay, so let's consider this as initial phase. So in first phase, we will bring this light at the origin. So in the first phase, we will bring the light at the origin, and we take the photograph, and this photograph will have all the model's depth in a data in a buffer. So buffer will save, buffer is saved. Now in next pass, now camera is actually it is drawing the scene, and now pixel by pixel it is drawing. So for this surface there is a red pixel. Okay, when there is a red pixel, it is saying I am okay. When it is okay, then it is going to light. Now we'll rotate the light again. We'll rotate the light again. First pass is over. We'll rotate the light again and we'll estimate the depth of the pixel, that is the red pixel what we are seeing. So in the final pass, first camera says okay, I am okay with the red pixel. Then light is transformed, rotated, and light is brought at the center, and then red pixel that is behind the scene, it is kind of coming in question again, and its depth value is calculated. Now depth value is referred in the texture. So depth value of the red pixel is 0.7. So 0.7 is here. It cannot be drawn. If it cannot be drawn, so there are three things. One thing is from camera, what is the idea about the pixel? If it can be drawn, it cannot be drawn. Next idea is light is coming at the camera and then it is seeing the red spot like this, and then its distance is measured. Third thing is that distance and again the placement in the raster where it is. So if it at the center, then it is already occupied as 0.4, but its distance is 0.7 because red color lies in the behind surface. If that is the scenario, then it cannot be drawn. If it cannot be drawn, then what can be done? I would say please draw it as black. I would say please draw it as green. I would say draw it as blue. My shadow is blue. I am a new inventor, and whenever sun falls on me, my shadow becomes blue. My shadow becomes green. It is up to me. Okay. So three things. One thing is first we generate this raster data, and then next time when we see any pixel that passes through the camera, primary camera, then we bring back the light again. So light is coming here two times. Okay, first time light camera is coming at the origin to draw the texture. Second time it is coming here to see the depth of the pixel from its own eye, and that depth and its location is compared in the texture what we have got. And then if it passes through, then it says the camera, then okay, it passes through, you can draw. If it doesn't passes through, then you can draw as a black, and then it becomes a shadow. Okay, so it will be followed by now real programming that we'll see. So we have covered shadowing in Opengl, camera and light source model, frame buffer architecture, depth buffer, texture map. Okay, so post we'll see shadow acne, means shadow may not be pleasant, what we want and what we can do. Okay, so we'll start. So before we start, I shall add one slide. Okay, so we'll make passes. Like first we'll create the texture. So from the light we'll kind of do the perspective or orthographic projection, and then whatever it comes. So anyway, as per the discussion, through GLU look at will bring the light at the center, but effectively it would be like from the light source, so we are making a projection, and then we'll have a kind of texture image, and in the final pass we'll see again. So first we'll see from the light source, and again we'll see from the light source, and per surface, per pixel we'll calculate the depth, and then we'll match against the whatever texture depth we see, and then we'll decide that it is candidate of shadow or it is not a candidate of shadow. Okay, so we can start. Okay, I'll create a directory called shadow map. Okay, so first we'll kind of copy one skeleton, or we need to type everything. We'll see if there is something already, text.py. Okay, so so we'll kind of delete everything, whatever we want, we'll keep it. So we'll have a kind of init and GL clear color and shade model flat, GL enable depth. Okay, probably we'll see this. Then we'll have display. Display is very tricky here, so I'm going to close everything, and then we'll have kind of keyboard. Okay, so probably I'll add that later. Reshape, big thing, and then this. So this is a kind of a skeleton code for Opengl and dpkg-l python 3. Okay, so python 3 Opengl we are using 3.1.5. So that is the scenario. So glut init and init display mode, we have single glut RGB. We'll add glut alpha. Okay, so we'll make it kind of 800 by 500. And okay, so it is shadow. So Opengl shadow. Display func display. Okay, so keyword we'll use, or we can just okay, so just mask it. Reshape and glut main. Okay, so we'll start filling it. So we'll have shaders now. So we'll import from the shaders from opengl.glut import star. gl dot shaders import star from opengl.gl frame buffer objects import star. Okay, and we'll do some computation. We'll import math, numpy as np. Okay, then import math from pil. We'll import image and we'll import REOs. Okay, so in the init we will kind of init is a big thing. So in the init we will have kind of GL clear color. GL enable GL depth test, very important. Now we'll have a frame buffer object. So equal to GL gen frame buffers. One will have. So we'll have kind of here global because we'll keep using it. Shadow texture, GL gen textures, GL bind frame buffer, frame buffer FBO, GL active texture, okay, so texture 0 will make it active. So by default I believe it is not required. GL bind texture, GL texture, (2D) shadow. So this is a texture object. So we'll make reference to shadow texture object also. GL text parameter I and GL texture 2D, GL texture min filter and GL nearest. So we'll copy it. We need not type again and again. So min and max. Please refer our texture tutorial for all this stuff. Min and mag. Filter GLS nearest. We'll copy again and we'll have wrap S. So in S direction how it would wrap. Wrap S, GL clamp to edge and wrap ST, that is in Y direction. So wrap T, GL clamp to edge, GL text image 2D, GL texture 2D, GL texture. Okay, so now we are kind of loading the image inside the texture object. So there is no image, so there is a special kind of hash depth, that is component, GL depth component, shadow width, whatever shadow we are, shadow height, GL again. So this is the formatting. Otherwise we should have used internal format and the image format as GL RGB or RGBA, but here it is depth component, GL float none. Okay, so shadow width and shadow height will. So here we'll say FBO equal to shadow texture equal to none, shadow width, shadow height. So we'll make kind of 256. So shadow width and shadow height, shadow width and shadow height, 0 GL depth component. Okay, now, so as we showed that in frame buffer there are many things that comes under frame buffer. So color buffer will mute it because we don't want, we are interested only in depth buffer to draw the texture. So we'll say GL draw buffer GL none and GL draw GL read buffer. So these are, they deal with color buffer. So if I set GL draw buffer and read buffer, then I can do kind of GL read pixel, and this kind of call I can make in the color buffer or the frame buffer. So GL frame buffer texture 2D, GL frame buffer, GL depth, GL texture 2D, FBO and 0. Okay, so now we are attaching. So GL frame buffer, GL depth attachment, GL texture 2D and FBO. Okay, so now we are kind of this Mr. FBO. So that we are kind of FBO would kind of it would generate a texture image. So that we have already bind. So FBO frame buffer and GL bind frame buffer, GL frame buffer FBO. So this texture object is bound. Now we say that GL frame buffer texture 2D. So it would generate texture inside where we have bound. So if there is any error, so we can print. So if GL check frame buffer status, GL frame buffer not equal to GL frame buffer complete. If that is the case, then we'll kind of we'll shout GL frame buffer complete ext field. Okay, so that will print if GL check frame buffer status, GL frame buffer not equal to GL frame buffer complete. Okay, now it's time to unbind it. So GL bind frame buffer, GL frame buffer 0. Now as we saw, so we unbound it. Now we'll have display. So we have display. Okay, now in the display we'll have, so if uniforms equal to, so now we will kind of load shader. So uniform is a kind of a hash, dictionary. So that is uniforms in the shader that is located. So at the beginning uniforms is like this. Okay, so that it checks, and if that is the case, then it calls load shader. So shader will be loaded in that fashion. Okay, so GL uniform 1I uniforms. So there is something called use shadow. So that will set to 0. So right now we are not bothered about kind of doing a shadow calculation. So this part we are not bothered. That is the final pass. Okay, so first we just concentrate on creating the texture, then we'll see the final pass. So use shadow will make it 0. GL bind frame buffer, GL frame buffer FBO, and then GL clear, GL depth, buffer width. Okay, reshape, shadow width, shadow height. So reshape, this function will get called, and GLU. So most important, GLU look at. So we'll have light position. So since it is used at many places, so we can just keep it. Okay, so the camera is in Y direction. It is pointing towards origin, and here it is located. So this is the grammar of GLU look. Quickly we can see. kind of like from opengl.gl import, we'll see if it is really there. GLU opengl GLU star. So quickly we can find like GLU look at. Okay, so this is the help of GLU look at. So IX, IY, IZ, then where it is looking, center X, center Y, center Z, and what is the direction of the camera. So up Y, that is what we are making. So Python has everything, means so quickly we can do. We can check. Coding time is much quicker than any other language. So GL uniform matrix 4FV uniforms cam matrix. So what we are going to fill, false NP transpose NP transpose GL get float V GL projection matrix, and then multiplied by NP transpose GL get float V GL model view matrix, and I think we are done. Now we will kind of GL load identity, and then we'll call draw. So draw function will, two functions we have to develop, draw and then followed by shaders, GL bind frame buffer and GL frame buffer 0, GL bind texture, GL texture 2D. Okay, so we are GL bind frame buffer, GL frame buffer 0. So it is like we did GL bind frame buffer FBO. So it's like okay, so we are done. Okay, so this portion I think I can just leave it, saving to a file, and first we'll kind of draw it and then we'll see. Now GL clear, so this is final pass. So texture pass is over. So generating the texture is over, and we'll go to final pass. Then again we'll have the same idea, and then from light and then from the camera. So we are nearing. So GL clear, GL color buffer bit, GL depth buffer bit, reshape shadow width and shadow height, GLU look at. Okay, so since we are doing same thing as we have stated, okay, so we are doing same thing, same projection matrix and same thing. So same thing we are doing. So we'll copy same code here. Okay, now there will be a bias. So idea is when we get the texture is kind of stored in 0, 1. Okay, so texture is lower left is 0 and then this is 1. This is how texture is. But now whatever we calculate, it is -1 to 1. So first we will make it half so that it will become -0.5 to 0.5. and then we'll add kind of some x, y, z 0.5, 0.5 so that it will become 0, 1. So that we call it a kind of bias. So I'll say bias. So bias equal to np dot array 0.5, 0.0, 0.0 and 0.0. Okay, so we'll keep adding. So 0.5 we are adding in the diagonal. So this shows that we are multiplying by 0.5. Okay, and now we are shifting 0.5, 0.5, then finally 1. D type equal to np float 32. Okay, so now we are ready for GL uniform matrix 4FV uniforms shadow matrix. So this will go in another calculation. False. NP transpose. So probably we can copy from here whatever we have written. So we are doing same thing. Again, okay, so NP transpose, and here we'll say NP transpose of the bias multiplied by NP transpose of the projection matrix and then model view matrix. Done. Story over. Okay, now we'll do GL active texture, GL texture 0, GL bind texture, GL texture 2D, shadow texture. Okay, GL uniform 1, uniforms shadow map. Okay, so we'll give a texture ID. So probably we'll give 0. This is what we are doing. And GL uniform 1, uniforms use shadow. Okay, so GL active texture 0, GL bind texture, shadow texture, GL uniform 1, uniform shadow map. So shadow map we are using 0 and use shadow, so we are enabling it. Okay, so we'll call reshape 800, 600. Now GL idea is that camera should be at the origin, but we are kind of little bit we are transforming to look better. GL uniform matrix 4FV uniforms cam matrix false. Okay, we can just copy paste one from here. GL load identity, draw glut swap locus. Okay, now quickly we'll kind of write the shader. Def load shader, global uniforms, program equal to compile program, compile shader, and now we can place uniform mat4 cam matrix, uniform mat4 shadow matrix, varying vec4 depth projection, varying vec4 color V, uniform bool use shadow. Okay, so now main will quickly finish. GL position equal to cam matrix into GL model view matrix, GL vertex, if use shadow, depth projection equal to shadow matrix into GL model view matrix, GL vertex, color V, GL color, okay, GL vertex shader. Okay, now I will type for fragment shader. Compile shader, varying vec4 depth projection, vec4 color V, and uniform bool uniform sampler 2D, shadow map, and uniform bool use shadow. Okay, so now void main float shadow equal to 1.0. If use shadow, vec4 shadow coordinate equal to depth projection dot w distance from light equal to texture 2D shadow map shadow 4.st dot z if depth projection dot w greater than 0.0 shadow equal to distance from light chord minus z minus 0.51.0 GL frag color equal to shadow into color V GL fragment shader uniforms cam matrix equal to GL get uniform location program cam uniform cam matrix uniform shadow matrix shadow map GL get uniform location program shadow map use shadow uniform location program use shadow print GL use program okay. Now we'll add draw function. GL push light position. So light position I have to declare probably light position 1 light position 2 okay. GL color solid K2 GL pop matrix GL push matrix, GL translate, GL color, select wire sphere, okay, so idea is to draw a sphere and that to map on kind of another cube, big cube. So GL push matrix, GL translate, 0 minus 20 0, GL color 0.5 0.5 0.51, color solid Q 40, GL pop matrix, GL push matrix, GL color 1, GL translate, at 0. So we are drawing one kind of plane. GL rotate minus 10, GL scale, glut solid Q, GL pop matrix, okay, so this is how it is. GL pop matrix, glut solid Q, and 40 minus 10, 18. GL push matrix 20.5.5.5 Q 40. Okay, and then we have GL clear color, so white, size 2, pop matrix, push matrix 10, blue color. Okay, so we are done. So light position will set. We have not set. Light position equal to 0, 20 minus 20. Okay, so I think I would describe this draw more when we see the output. So kind of it is more rational. Okay, so vertex shader has a compilation error. depth projection, color V, use shadow, cam matrix, GL position, if use shadow, GL color, shadow matrix, depth projection. I think it's all right. What about this? Depth projection, color, shadow map, and then use shadow, shadow, use shadow, depth projection, distance from the light, and if depth projection, then 0, then light, GL frag, shadow, color V. I believe it's all right. Okay, glut, bias not defined, GA uniform not defined, uniforms not defined, and we get it. Okay, so I believe I have not resized it, but this is how the output is. So we can see kind of one wire frame, and light should be visible. Yeah, so it's visible. So this is light source, white color, and it is placing light. So the camera is not at the origin. Okay, so camera is also at some height, and this is the shadow we can see, and then kind of so we will change the light position. So this is one surface, we can see this is one surface, and this is a table kind of. So sphere is kind of in sky, and then light falls on the sphere, and we can see the shadow. Okay, if I move the light here, okay, then shadow should come here. Okay, light is at 20 and minus 20. Okay, so 20 is y and minus 20. So idea is that light will move it to 20 minus 20. So we'll see if it comes. Nice one. Okay, so if light is here, then it falls on this surface and this surface. Okay, we'll kind of make light source minus 20 is, I believe it's all right, or make minus 40 or 20. Okay, what I'm trying to do is okay, so we'll reduce this. Now we'll see. Okay, so we can see the light is, I want to bring it on completely on this plane. So this is what I'm trying. Probably I'll make it even less. I'll make it more. Let's see. Wow. So light is falling, but we can see this is, so we'll make the angle more. We'll see GLU perspective. It is 45. So what we are trying, we'll make it 60 so that it will be broader. Okay, so origin is somewhere here, so we can see shadow falling on this. Okay, so this side, so when camera is here, then it is looking at the origin. So when camera is here, it is looking at the origin. So this is coming as a kind of sideways. It is not looking at the sphere. Okay, so that is the scenario. Okay, I'll try to bring it near if something changes. And some 5. Okay, height I believe I can decrease. I'll try. Okay, so it is not showing, means it is not coming the pixel. So what camera is kind of is seeing, so that will try to kind of make it. Okay, so minus 20, and then we'll make more. We'll try minus 10. Okay, so shadow is falling here. Okay, so now I think it's okay. So now we'll show the code and then we'll proceed. Okay, so in the code we have light position and then we have shadow map. So in this directory we have only this program, text.py. Okay, if we want a bigger picture, then we'll make it small again, kind of 45 or try 30, how big it would be. Okay, so certainly it is more clear, but our light source is not in the view. This is problem with VLU perspective. We'll try with 40. Okay, certainly it is better, but again our light source gone. Okay, so we'll try 45 only. Okay, so I believe it should not be unhappy much. Okay, so better. So light is falling on this sphere and then it is getting drawn here. Okay, so more I'll shift it to, so that shifting we'll see. Now we will kind of see the code. So so we have a frame buffer and then we have one texture object, and then texture object property we are assigning nearest. Okay, and then we have a kind of texture object loading of the image. So instead of loading the image, we are specifying it is depth component and shadow width, shadow height, and then it would fill the value as float. So that is the idea. Color buffer we are kind of shunting it, and then we are kind of generating the kind of saying to generate the texture. So texture is bound to this frame buffer, and then we are unbounding the frame buffer, unbinding the frame buffer. Now we are drawing cube first, that white cube, that is the light source that we saw, and then okay, so we are shifting minus 20 and we are drawing 40, so that is a table where the shadow is coming. So that we are trying. There is one more. So this is light cube, and then this is the wire sphere, blue color, then this is the table, and this is the yellow color plane on right side that we are seeing. Okay, now in the display, first we load the shader and then we bind the frame buffer, and binding the frame buffer we first generate the texture map. Okay, so that is the idea. Okay, so uniforms use shadow. Okay, so that we will see in the texture. Now we are saying look at, and then we are filling the projection matrix. Can we see like the projection matrix and model view matrix that we are multiplying, and we are setting as a CAM matrix. Okay, and then loading identity and we drawing it. So whatever we are drawing, it is coming into frame buffer, and whatever we are drawing, so that drawing is happening through the shader. So we have kind of two matrices, CAM matrix and shadow matrix. So initially we don't use shadow. Okay, so only CAM matrix. So CAM matrix in the sense that light we are behaving as a camera, and we are doing GLU GLU look at. So CAM matrix we are filling. So this is simple, this code is not getting executed at all, use shadow. So this is for final pass. So for the creating the shadow to create the shadow texture, only this line is enough. So CAM matrix, whatever the current projection and model view, that we are multiplying and setting it in CAM matrix. When we call draw, whatever is the new projection, and that anyway that is new model view, that is coming in model view matrix, and whatever the vertex is. Okay, and there is here at the beginning only we have used shadow, so there is no meaning now. So when we trying to draw the texture map, only this line is valid. So CAM matrix and model view and GL vertex. So whatever we receive, so that is placed inside the texture, so that we'll see how the texture looks. Okay, then we can tweak more the light position. So what we are doing is, first we are reshaping shadow width and shadow height. So reshaping is nothing but setting the viewport and projection load identity, and then we are setting projection as GLU perspective, and then GLU matrix board model view and GL load identity. So reshape is nothing but kind of setting the projection matrix and loading the model view and setting the identity and setting the viewport. So first we set all those steps. So this is the simplest possible line of code that we have written. Okay, it is kind of will be much bigger at other places. So it is a kind of a place where it should be referred. Okay, so reshape, shadow width, shadow height. So model view is load identity. Now model view are filling at through GLU look at, and then GL uniform matrix. So here the CAM matrix in the shader we are filling as multiplication of the projection and model view, and we are loading the identity. So whatever we have filled in the CAM matrix, so now our model view is completely empty now, and then we draw. So if we call draw, then it would refill the model view. So this is okay. So if I say GL load identity and then call the draw, then it would refill a complete model view matrix again, and whatever it refills, if we go to shader program, then CAM matrix anyway we are setting as per the kind of camera matrix, that is the light source. So when we do the look at, okay, so when we do the look at, then this light source we are transforming at to center. Okay, that is the look at that we have seen. Okay, so this is the CAM matrix we are setting after look at. Then we are then model view matrix, that is the draw function what we have seen, and vertex. So vertex, model matrix, and CAM matrix multiplication of the projection and the look at model view, and this we'll see. So this is what we have done. Okay, and then we draw and then we unbind the frame buffer. So idea is that since we have called the texture 2D, we have called the frame buffer texture 2D. So frame buffer is bound to draw everything into the texture. So depth value is coming as a texture pixel value. Now we are clearing the color and depth buffer. Okay, and we reshaping it, calling GLU look at, and now as we talked that the image what we get the texture, so that is 0 to 1. The image is 0 to 1, not minus 1 to 1. So whatever we generate. So again we are kind of doing reshape, and then GLU look at same light position. So this is the second pass. So first pass we saw a frustum. Inside the frustum we are creating the texture map. In the second pass again we are calling same thing and trying for each pixel we are trying to get the depth value, just depth value. So bias is required because so bias is required because we are converting. So now whatever we are drawing, that is in minus 1 to 1. So first we convert it to minus 0.5 to 0.5, and then we will add some kind of translation, and so that it will shift minus 0.5 to 0.5. So we'll add 0.5. So it will become 0 to 1. So that is the kind of biasing. Okay, so 0.5, 0.5, 0.5 is making it half. This is identity kind of matrix, and then we are setting the bias 0.5, 0.5. So first making minus 1, 1 as minus 0.5, 0.5, and then minus 0.5, 0.5 to 0 to 1. So that is the idea. Once we do, then again we go for multiplication of this bias, and then projection, and then model view matrix, and we set it to shadow matrix. Okay, so and then after that time comes for the final pass of the actual camera. So these are light camera, actual camera. So first the shadow texture what we have received, that we set, and then we enable the use shadow. So use shadow is 1 now. Okay, and shadow map. So there are please refer kind of texture tutorial. So there we have texture units. So we are enabling texture unit 0, and then we are enabling use shadow, and then we are reshaping with our window size. And then we are shifting the actual camera also at 60-60. Later we'll try to place it as 0-0. This is what the actual design is. That camera should be at 0-0 fixed. But this also we have kind of, to look better, we have shifted through GL, not required. And then again we set the cam matrix and transpose model view, and then load and then draw again, and then glut source. So when we drawing again, now pixel by pixel it is drawing. So if red color is the pixel, then for this pixel we draw all the kind of analogy that we have shown. Okay, so that is the idea. Now if we go to kind of shader programming, then we are enabling the use shadow. If we enable the use shadow, then we are calculating again same thing what we did in cam matrix, shadow matrix. So here bias into projection into model view, and model view matrix would come from the draw function, and depth projection, this is how we get, and whatever the color we are getting, the color we are setting through the GL color. And in the fragment shader, what we do is that the texture value whatever we receive, so in the texture value we read the each texel value, that is the distance, and whatever we receive. So there are two things. One is the texture value that is stored, and second thing whatever the distance we are getting in the second pass. Okay, so this is the distance in the second pass, that is shadow coordinate, and distance from the light, that is from the texture. Now if texture is less than shadow coordinate, okay, then the object is on right side, so it should be shadow, that is 0.5, okay, and otherwise it should be kind of white. And then fragment color we set whatever shadow we are getting with the color we. Okay, so as we discussed, so this is 1 we are setting, so 5 we are setting. We can kind of a shadow, or we can set a color also, or we can kind of set it as okay, so we can change the kind of intensity of the shadow. So in shadow would look kind of less gray. So that is the concept. And then we set all the uniforms to whatever uniform location we are setting. We have printed it also. That's it. Now we will kind of move the light source and then we'll see how it looks. So this is the smallest possible line of code in the kind of in shadow. Okay, so this is the concept. So we'll go to initial and we'll see the output. This is our 30, we'll keep it. Okay, so this is the initial output and Mr. Light source is missing because we set it again too high. Okay, so we'll make it really. Okay, so light should appear. So this is light source. Okay, and it is falling and this is the shadow. So the shadow acne that we will discuss later. So can we see that these are the lines that are coming? So these are unwanted things that we are seeing. So that we will cover to how to remove these lines and how it appears. Okay, so now we will kind of we'll add more features to it before we can kind of concentrate on the shadow acne. So it's not a bad idea to kind of rotate the light source so that it will be kind of little bit animation and we can see that. So we will kind of uncomment it. So and we'll introduce the keyboard function. Okay, so light position we are going to modify. So global light and then if R is search. Yes, Python has everything. Whatever you need, it's there. Best regular expression. Light position. Okay, so we will kind of make up, down, so 2. If key equal to up, else -2. L if up or it is right. Then in this case we will kind of X will shift and then we will say near and far and then we'll modify to near is first. Okay, so glut post redisplay and done. So based upon the keyboard we will kind of modify it and the light position. So light position is at the beginning, so very nice. And once light position modifies, then our light source would change and we can see the kind of light moving. We can try it. Okay, so light source is available and idea is I can move the light. It's moving. This is what I wanted. Now shadow is on this plane. This is the shadow of this. So see the shadow acne is more prominent. So if I bring it down, can we see as it is becoming, if kind of the shadow is growing. It is going in X direction. Acne is growing. See how big acne is. And it is becoming smaller. The way the light source is. Anyway, I think it's nice to have this moving kind of a little better. So we'll have kind of one more guy. So we will implement it. So we can say a window width, window height equal to 800 by 600. So at the beginning we'll set this, and then we will do some kind of tweaking. Okay, so here in reshape function I'll introduce mode. Okay, something like none at the beginning. And okay, so once all the kind of work is done, I can say window width, window height equal to, if not mode, okay, else window. Amazing, means no one can believe like someone can write code like this. Window width, window height equal to WH, if not mode, else window. Amazing. Okay, so this is done. Now if reshape is called by the kind of Opengl code, then mode is none. So if that case, it will reassign the window width and height. Okay, so we'll say it is global. Window width, window height. So Mr. Width and height are global. So we can modify it. And now here when we call it reshape, then we will add parameters. So I can say here shadow means anything. Anyway, we are not checking it. Reshape mode equal to shadow, and again reshape. We can say something like window. So these are the kind of I can grep on the reshape. Okay, so if reshape is called by ourselves, then we are passing extra parameter. Okay, so we'll try now. So okay, so 800 will search. So here in the final pass we are calling 800 by 600. Now it is window width, window height. So what we are trying to do is that we'll remember window width and window height if it is kind of called by the system, and then we can kind of call it again. So if it is from system, not mode, then we modify it. We'll try it. Okay, now I am going to maximize it. Far better. This is what the imagination is. Okay, so now it is better. Now I can rotate the light. So white cube is light. So light is going on the next surface. So this is shadow of this wire sphere, and if I move the light up, then shadow will come on the table, down it will go to, okay, so full-fledged it is making the shadow. Okay, I can bring it near, then shadow would move behind. So this much. Okay, so more we'll see. So why it went away. Okay, so I mean, it is in documentation that it is a matter of research, but I little bit disagree. Means if you kind of understand the nuance, kind of miniature Opengl. So every nuance of the Opengl, then you can crack it. Means it's not that difficult. Okay, so amazing. So it is making the shadow, one thing. Second thing is, can we see the shadow icon? This unpleasant shadow is coming up, and this unpleasant shadow is everywhere. I mean, I am going to replace it with so where I'll say solid. On the sphere also it will make. I don't know, it is visible here. Okay, looks like it is not making. So thank you, it's making. Okay, so I mean it should be more visible if I have no idea how I can get. I have not put that provision. So GLU perspective, I can make it little kind of 30, and then light position, this will make it smaller so that it should be visible. I hope so. It's visible. Shadow acne is getting formed on spheres. Can someone see the change in the sphere? So, see, it is covered now. See, it is changing. Okay. So this is the problem. Means it is prominent. Shadow acne is prominent now. So the idea is how we can reproduce this. If light is kind of horizontal to the, means if y axis is less and the shadow is kind of larger, then shadow acne would be more. If it is perpendicular, then it will be less, smaller. Will be smaller if it is exact perpendicular. But if it makes angle, if it makes more angle, then it is more prominent shadow acne. Okay, so this is the kind of unacceptable. Okay, so you are achieving something, you are earning kind of $10 when we are wasting $1,000. So it is something like you are achieving something, but you are losing much. Means who will accept this? No one can accept this. So in the name of shadow, we are getting this much in reward. Okay, so that we'll tackle later. Now the question arising is that whatever the light is seeing, okay, so when light falls on the sphere, means there is no lighting anyway. It's a complete mathematics, and it is just matrix multiplication. But still, when light is falling on the model, then how it looks from the light perspective. If I take a photograph, okay, so if I bring a cameraman, if I bring a photographer, and then it's a kind of it's impossible to find anywhere, means how to take photograph. So what light source is seeing, so how to take photograph? Okay, whatever we are seeing now, so nice, means whatever we are seeing now, that is from the camera. So camera, we have done glut load and we have shifted the camera from the origin. Okay, so in the code, if we see, so if in the code, if we see, okay, so my 6060, we have shifted the camera also. It's not at origin. Okay, if this is the scenario, so whatever we are seeing, that is from camera perspective. Okay, now when it is making shadow, how light is seeing means I gave a hypothetical kind of analogy, light is seeing like this. So hypothetical we gave, like when light is coming to the center, then it is giving something like this. Okay, but I don't know, whatever we are seeing, that is from the camera perspective. What is from the light perspective, that we don't know how it is taking the photograph. So as I said, all are our local code. So we'll try writing it. So how it would happen. Okay, now we understand that whatever the frame buffer is drawing, that is getting captured in texture object. So there are three things: frame buffer, texture object, and the memory. So at the memory, image is stored, so that we upload through GL text image 2D, but anyway there is no image, but texture image is ready. And second, so one is memory, one is texture image, means texture object, and one is frame buffer. So in frame buffer, when we talk about the image, then mainly it is color buffer. So that mainly we discuss. So that is the color buffer. But anyway, I think it's understood that color buffer is muted. It is set to null. So that whatever frame buffer is drawing, so we have attached the frame buffer, GL depth attachment, to the texture 2D. So whatever the FBO, so we have bound the FBO, and then we have done all the great thing in the texture object. So this texture object is bound to this FBO, and then we are saying explicitly that FBO should be drawn on the texture object. Now, if we have texture object, so this proves that things are getting drawn on the texture object. So if that is the case, then can we texture object can we put on the kind of magnetic tape so that we can see it. So can we place on reel the texture object so that we can see it? So now in the first go we are creating the shader. So here when we unbound the frame buffer has already copied the texture object. So frame buffer did all the camera stuff, it did all the recording, and when we unbind it, means GL frame buffer 0, so texture object should be ready by now. And in this case we are happy that now I'll say bind texture. Okay, so GL texture 2D and shadow texture. I'm not going to make it global because it is read only. So I think it's okay. Okay, now I will say okay, texture image or temp texture image so that it should not collide with anyone. And then we'll say GL get text image. I don't know there is a help or not. Python 3 from Opengl.gl import star. Okay, and help in the GL get text image. Okay, so return the pixel data array in the format defined by the format type and output type. So whatever is in the texture buffer, so that should be returned now. So that is the idea. And then we have to place all the grammar what we want. So GL get text image. Okay. So GL get text image and GL texture 2D 0, GL depth component GL float. Okay, so GL depth component is a kind of type we are using. Otherwise we could have used GL RGB, GL RGBA like that. But this is for the depth that we are using. GL float is float. GL float we have used. So this is GL float. So if it is very far, it is 1. Otherwise, so everything is kind of normalized between 0 and 1. So that is GL float. Nice. So GL float, GL depth component 0, GL texture 2D. Okay, now image from bytes. So we are going to create image, and this image is a kind of bit image. I mean it's a kind of monochrome image based upon the gray level, not in RGB value. Shadow width, shadow height will convert bytes, and the way Python is, you can write a big thing in so small. So 100 into 255, I'll tell you what we are trying to do. For X in temp texture dot reshape 1 shadow width shadow height transpose image flip top. I mean there are languages to do shorthand when you write many things kind of. So I'll say depth shadow texture dot png. Can someone believe this is Python code? Okay, so what we are trying to do is, from bytes we are creating the image format is L, shadow width and shadow height is the image width and height, and then data what we are receiving. So for X in temp texture, so temp texture is a array of width and height, so we reshape it 1 into shadow width and shadow height, so it will become a kind of single row data, and then we fetch the data completely, and then whatever data we are receiving, so that data then we do power of X into 100, so all the data is in point maximum 1, so it's completely alright. So if data is near means 0.5, then it will become even smaller. So data is bigger, it will be bigger, data is smaller, so this is what we are, so that it should be visible. Whatever we are achieving, then we are multiplying by 255 so that it will come to grayscale, and then end. Okay, so there is no boundary here, so I believe it's alright. From bytes, and then we transpose it top to bottom because image is shaped. So origin in the Opengl is bottom, where image origin is on top as per the image fundamentals. Save to depth shadow. Amazing. Means it is mind blowing. No one can do it. Is it too much? I mean, it's okay, means it's done. That's it. So what we did is, once the frame buffer is unbound, then we bind the texture, and then we get the texture image. Okay, and texture image is finally then this much we do, and to get there. So we'll try again. There is no harm in trying. So there is nothing, only file is there. Okay, so it looks like it is showing error. Temp texture is not defined. Temp texture image. Okay, so temp texture image is what we meant. Image is not defined. Okay, so name image is not defined. Okay, I mean, we expect something now. So I'm closing it. Image is ready. Mr. Nemo. Image is ready. Can you believe this? So this is wireframe on top. I mean, there is no harm in enlarging it. So nice. So this is the actual black and white photograph that used to happen, I think 30-40 years back. And so this is what it has taken. So the top is white, what we see. White means this is the end, and then down it is the table that we have drawn. Then so nicely it is come. Okay. Now we'll keep moving it, and then we'll see. Okay, so Mr. Nemo is not happy. Okay, so idea is that we will move it, it is moving. Okay, so we'll add one sphere so that it will be more prominent. GL push matrix, GL color will make it red, and GL glut solid sphere, and radius 1 will keep it small, and GL pop matrix. Okay, now we'll try to get it. Okay, we can see clearly red spot. So this light is pointing on the red spot, and in between it is saying this sphere, wire sphere, and it is creating the shadow. Now we can rotate the light. Okay, so from this perspective, light will come on the red spot. So this should come, I believe, on the left side. Okay, so this is how it is. So right side it is showing complete white, and it is showing top around center. So when it is seeing the right side, this is the sphere, this is light source, this is center. So on the right side it is blank, so value is coming as white, top right. Okay, and bottom anyway table is there, and table is near, so it is dark, and up is the yellow one, so it is kind of far, so it is little whitish, and then this is like this. So if I make it come near, okay, so it is seeing the red spot, and then I think this is exactly on top of red spot. So that's why it is coming in the center always. So we'll try to move on in the left side, so that we'll see. So we'll translate it to kind of minus some 10. Okay, now light will move. Now sphere is seeing the red spot, and this is coming on the left side because it is minus 20 now. Okay, it is not only y directional up, it is behind the sinos. So it should come on left. It is exactly coming in the left. Can we see? Okay, so this is how we can take a photograph. Okay, so what the light source is seeing. Now the light source and this red spot, they are in line. So this sphere should come in the center. It is exactly in the center. It is auto refreshing. It is exactly in the center. This is how it is. Okay, so this is how. Now only item that is left before we start the shadow acne, this raster data. So whatever the image we are drawing, so that image can be stored in a file. Okay, how we can see, because this is a PNG image. So for that we'll write the code. So we'll say like file equal to open, okay, shadow raster dot text, and then for row in temp texture image, file dot write join round x 4 or 3 for x in row, file, okay. So file open shadow raster dot text width, and then we are trying to do some magic, and we'll see now. So we'll close this. Okay, so now there is nothing here, so we'll try to make it. Okay, okay, so that is gone. Okay, this is the last thing we are doing. Temp shadow, okay, so row in temp texture image, file dot write for x in row, file dot write star dot join Okay, so we'll make it a string. Okay, so we'll try. It will be slow now because it is writing to the file. Okay, so it is slow. Every processing is slow. It is slow because it is writing to the file. Okay, so we'll have now file and shadow raster text. So this is the raster image it is generating, the way what we are discussing. At the bottom it is 1. So the bottom frame is white. So that we will see it is really white. Okay, so top is white because image is upside down, the way Opengl and image fundamental works. Otherwise, this is what we expected. Okay, so we generated image and raster data all. Since every moment it is creating the image and then file, so it will be slow. Okay, so we'll proceed on much awaited shadow acne. So we'll add slides for it. Okay, so as per the discussion, shadow acne is something like whatever the undesirable, the lining what we receive. So I think I have, or I can show it. I can, so we don't need it, so we will kind of comment it. Okay, so shadow acne is visible, and as light comes flat to it, then okay, so this is shadow acne, and it is different on this table and on this yellow plane, so that is visible. So same thing what we can see here. Shadow acne generated while drawing the shadow, and acne width is proportional to the angle between light source and shadow normal. Okay, so if this is light source and this is shadow normal, so this is normal, so shadow is being drawn on this surface and shadow is being drawn on this yellow surface. So this red color what we see the mark, so this is normal from the yellow surface, and this red color whatever we see the mark, that is normal from the table. So whatever the light we are receiving, so this vector, the yellow color what we see, so this angle, I think angle is prominent, so this angle, so if this angle is more, then acne will be bigger. If this angle is less, that we can see it is less, so this acne will be smaller. So this is what is been seen. Okay, I think we can see that. So we will kind of change -10 back to 0. So it will be above only, and then we will try. Okay, so if I bring it down, it will be bigger, that we can see. Okay, so if light is falling on a surface and the angle between light and the surface normal is high, then this acne will be bigger, and if it is falling on this yellow surface, then normal is, and this light falling, the angle is very less. So we can see that acne is, the distance is less. Okay. Okay, now we'll understand the mathematics. So if we see the code, so there is a final pass in the code. Okay, so first we generate the texture. So first pass we generate the texture, and in the final pass, from the same light source location, we see the kind of the surfaces again, and then we receive kind of 3 coordinates per pixel, x, y and z. So x kind of x and y -1 to 1 range we get, that we slowly transform into 0 and 1, and whatever z we receive, so that is the depth. Okay, now with x and y, what we receive in the second pass, that is kind of indexed into the shadow texture that we receive in the first pass. So it will come to xy coordinate where it is, and whatever value we receive, that is the depth. So that value will be compared against whatever we saved in the texture. So that is the idea. Now, like if I have a kind of model view matrix, that is identity, then I say GLU look at. So we modify the model view matrix and then we add the bias to convert -1, 1 to 0, 1, and then we change the shadow matrix in the shader code. So if we see the shader code vertex, then we have kind of shadow matrix, that is the kind of projection matrix and multiplication of the bias, projection matrix and model view matrix, and then model view matrix what we draw. So and then what is the vertex. So if we combine all three, so if I call at the end draw, and then if I see the function draw, then we do lot of translation. So this would change the model view matrix. So first shadow matrix, so if I see the vertex shader, then shadow matrix, so shadow matrix is nothing but initial projection matrix, bias and model view that is received from the GLU look at. So that is it. And then whatever, while drawing whatever the translation and rotation we do, and the GL vertex. So this is the vertex that is kind of, we think if the model is kind of kept at the center. So model is kept at the center, and then whatever GL rotate and translate we do in the draw, and then whatever the projection and translation we do through the GLU look at. So all three kind of we multiply to get the depth projection. So depth projection X and Y. So depth projection X and Y would kind of map into the texture buffer. So then we'll come to a conclusion that which point it is pointing in the texture buffer, and then the Z depth. So depth is kind of it is finalized. I mean, if there is a battle, then there is a finalization. So depth is finalized. So depth is finalized in a kind of, so we see, so depth projection. Okay, so this is not the equation. I believe it is wrong. Okay, so shadow coordinate dot Z. So depth projection dot Z. So we'll modify it. Okay, so we'll add dot Z. Okay, so we will add dot Z. I hope it would nicely fit in, or I'm going to shift it. Okay, so I saved it. Okay, so whatever the ST, so depth projection ST, X and Y, we map into the texture 2D, and then we receive some data, and then we compare with the depth projection Z, and if the item, so it is like whatever, so okay, so these are the data that is found in the texture map. So that is this, and then whatever we receive in the final pass. So in the texture making pass we get the texture, and final pass with the XY coordinate we try to see the data. So if the data is bigger, in the sense that like if this is the model, that is the nearest for this pixel, and then we are drawing somewhere here, okay, then this Z from the light source is higher to the Z depth that this sphere enjoys. So if that is the case, so if texture is less than this, means if this project is higher, then it is shadow, otherwise it is not shadow. So whatever color we are receiving, so that color will be faded. So that is kind of analogy we are using. Now if we go to kind of in-depth, now every kind of model, so generally it will have some primitive to draw it. So if I am using primitive GL triangles, then model is a set of GL triangles, means there are many GL triangles. Okay, so okay, so there can be many GL triangles. So if I take a sphere, then in the sphere there are many GL triangles. So one is Mr. Triangle this. So it is made of GL triangles. Okay, so it is like this. Okay, so this is like this. I mean, I can keep it somewhere. I can keep it here only. Okay, so this is like this. So one triangle I am taking. So this is how we make the model. So it's a kind of series and or it's a kind of mesh of triangles. So one triangle I am taking. So inside one triangle it is set of pixels. So this is the kind of in the second pass. So second pass, there are two things. If I see the source code, okay, if I see the source code, then there are two things. So this is first pass. So first pass is passed. In second pass, we kind of we do all the multiplication and we update the shadow matrix in the shader, but we don't draw it. And then we set the texture map, and then we set cam matrix, and then we draw it. So if I see the shader, okay, so vertex shader, then in vertex shader, there are two matrices, cam matrix. So in a final pass, the cam matrix is the actual camera matrix, and shadow matrix is the light matrix. Okay, so there are two matrices. So GL position of the pixel is the camera matrix and depth projection we are receiving. So when we see any texture, then we do texture 2D. So texture map is the actual texture, and this is the XY coordinate that we place inside the texture 2D to fetch its value at that location. So in this picture, the kind of texture sampler, okay, so texture unit. So texture unit is a guy, please refer Opengl texture tutorial video. So texture unit is kind of it's an entity which refers to a texture object, and based upon the ST coordinate it fetches the texel. So texel is nothing but depth texture, so depth value, so that we receive. So that is the idea. Okay, now in the triangle, so whatever triangle we see on the sphere, so it has set of pixels. Now if we see the texture generated, then same triangle we can place, but these are the green colors are texel, whereas these yellow color are pixel. There are two things, pixel on the screen and texel what we see in the texture. So density or resolution of text cell and pixel, certainly it will be different. Okay, I mean, I can do lot of mathematics to make it same, but it can be different. Now if I merge these two, then in the second pass, when from the light we try to get these values. So like I am drawing a pixel on the surface, that red color pixel, then that xy or st coordinate would map inside the texture, and then finally we received the depth value. Okay, so when we talk about in the texture map, when we kind of map the xy value, so that is the textile coordinate, so that is between 0 and 1. So it would map these three textile coordinates, some arbitrary, one textile coordinate in the xy direction, other textile coordinate in the three corner, and other. So in the second pass, whatever we are drawing, so that would map in the texture at the three corner, and then we bring the kind of bunch of pixel inside that, and then other textiles, it would not match. Okay, so pixel density is higher and textile density is low in our case, I mean other cases that we can think. So shadow width and shadow height is 256 by 256 pixel, whereas we take 800 and 600 in the same area. So this is the big window we have taken. I mean, mathematics may not be related, but this is how it is. So the density would not be same. Now if we see the kind of a texture and pixel mapping, so that comes under MAN and MIG, so minification and magnification filter. So here it would be magnification because the textile density is less. We choose the nearest. So pixel, so there are a lot of pixels. So each pixel value for the coloring. So when we go from vertex shader to fragment shader, so vertex shader is talking about okay, so kind of three vertex. So it has three vertices. So this is not I have drawn. So but I can show it. Okay, so if we see the kind of vertex shader, then cam matrix is GL position. So for a particular kind of drawing model, or we can say drawing primitive, for GL triangles, three positions would come. Okay, and as per the three position, depth projection also will have three positions. So this depth projection is nothing but texture coordinate, but this GL position will be the pixel coordinate that I have not drawn. So whatever I am showing, so this is the textile coordinate. So textile coordinate would map inside the texture, actual texture, and then it will map the three textiles. Okay, so now inside that three textile, because of Mr. Cam matrix GL position, the three vertices, so it will now get the actual pixel inside it. Now pixel and green color is textile, so pixel textile relationship will start happening. Now we are saying the min filter or mag filter. So here it is mag filter. So lot of pixel would map to one textile and it is the nearest. So I can say I have put in a circle. So these many pixel would now, they would kind of refer to the same textile and it is nearest. And if it is nearest and they refer to same textile, then the pixel which are the depth of the pixel which is greater than the textile. So right side if I see, then the depth would be greater. Left side depth would be less. If it is less, then it is bright. And if it is right side, then it is dark. This is what we are saying. So what is the problem? Inside the same triangle, there are so many triangles. Okay, if I see the sphere, then there are so many triangles. In each triangle, at each textile, there is a region where it is white, there is a region where it is black. And now, so this is for this textile. if I talk about this text cell, then again left side is bright, right side is dark. So inside a triangle, we see white, black, white, black. So light and shadow we are seeing inside the same triangles. So if this is the shadow, if this is the surface, then we are seeing white, black, white, black, white, black. Means in miniature science, if we understand textile pixel, then inside the same triangle, GL triangles what we see, at each textile we are seeing white and light and shadow. So this is the problem. Means, so even if I increase the density of the textile, it would not match per pixel way. I cannot go for that kind of mathematics. Okay. If someone is good at mathematics, then he can try mapping pixel and textile. And then, so interpolation happens. This is what I was trying to say. So, if if I know the depth at these vertices, then this pixel depth, so many pixels are there. So this pixel depth would be interpolated, and that interpolated would be not the same as this textile. So there is a problem. Okay. So this problem can be because of we use nearest, we can use linear. This problem can be because of the image what we take is less density. We can make 512, 1024, 2048. Okay. So in those cases it would differ. Okay. Anyway, screen pixel resolution I can't change. We can do some mathematics to make it kind of abstraction change. So that can be done. Okay, I believe through kind of depth reshape. So viewport width and height would do some magic. Okay, so I would now draw it, and something I'll try to change. Okay, so this is the beginning. This is crystal clear. So let's see if beginning is changing. So this is the beginning, and then I am going to, so nearest I'll make it. Okay, so as I say, everything is crystal easy in Python. So commenting is also very easy. So GL nearest, I can say it as linear. Okay, let's see if really changes. Okay, I would say it's different. It's certainly different. Now, if we see the acne pattern, then they are different. Which is left, which is right, I don't remember. But it is different. Even shadow is different. Okay, so I believe this is the nearest because we can see lot of differences are there. With a linear, it is smoother, but problem is there with both model, linear or nearest. So that is not the solution. Okay, I am going to delete this and revert back. Okay, so okay, now I am going to change the texture size. Yes, comments, just put hash and amazing 1024 and 1024. So I am making it big. I believe 4 times bigger. Let's see if it is changing. It is different. Can we see? Again difference. Now acne is smoother. Here it is coarse in 256, but the shadow is gone for toss. Okay, so we can see. Okay, so here it is better. Okay, again we have to think about so many permutation and combination. Okay, but anyway, we'll revert back to 256. No need to do too much. No need to apply too much brain. Okay, so now we understand why it is kind of continuous black and white. What is the solution? So solution is whatever the pixel that is on right side of the text cell and that is coming under the GL near of the, because beyond this it would come under this text cell and this text cell. So whatever this text cell is covering, so that region, if it is in right side, then we will we will subtract with some delta, okay, some delta distance, and so that this text cell, these pixels would appear on the left. So if this pixel is delta x on the right side of this text cell, I will decrement delta x so that it would appear at the pixel or left side. So whatever we see on the right side, so it should go on the left side. If it goes on the left side, then it will be completely white. So again, for this text cell, whatever comes on the right side, full right side we will shift in the left side. But what is kind of other way of consequence? Then the image would shift, shadow would shift, because text cell by text cell we are shifting like this. Slight shift will be there in the shadow and the image. Means this is the downside. Okay. Now how much is the delta distance? We have to think. Now let's see the kind of projection analogy. Now if I see the projection, okay, so depth, reshape. So if I see the projection, we have used GLU perspective. Consider I am using GL ortho. If it is GL ortho, then the distribution in the depth wise, it is kind of consistent. So now if it is kind of near plane and if it is the far plane and L is the distance, then we normalize L to 1, because this is what we have seen, that 1 is the maximum distance that we see in the texture. But why this is 1? Because when we create the texture, at that time we set it as GL float. If I set unsigned int, it will be bigger. Okay, so we set as GL float. We set GL float. Okay, so if we set GL float while loading the image as GL depth component, then in the format, then it would be maximum 1. So 0 to 1 it would normalize. Okay, so that is the concept. So whatever the distance near and far we are taking, that we have to normalize it to 1, means it will be normalized. Now, okay, so if we see this diagram, the kind of we have seen, we have taken kind of in ortho, it's a frustum. Okay, so it's a frustum. So if I see the frustum, then this is the far plane on which the shadow would appear, and this is the surface. Suppose in this on the surface, that is a sphere, any point is at distance L1 from the light source, and any point on the surface where the shadow would come is L2, and total distance is 1. Okay, so L2 and L1 from the light. So in the frustum, now I need to normalize L1 and L2. That would be L1 by far minus near, L2 far minus near. Consider far minus near is 300 and we have taken 300. Okay, so we have taken 300, 1 to 300. Or if I had done GL ortho, it would have been 1 to 300, means it was 300 everywhere. So far minus near is 300, and light, suppose that kind of, okay, so this light source is kept minus 100 in the Z direction. It is at minus 100. Okay, so that is not the case. Light source is at minus 20 in our example. Okay, suppose it is minus 100. Now L1 is at minus 40 and L2 is minus 2. Now if I normalize L1, it is 60. Minus 40 means it is at distance 60 from the light. So 60 by 300, it will 0.2, and then L2 will be 0.266. So the distance between surface and model and the surface on which the shadow would be drawn. So that would be this minus this, that would come as 0.66. So if gap is 20, then the distance, normalized distance is 0.6. But in practical sense, this triangle will be very small. Okay, so it will be much smaller than 0.6. But this is the analogy. We are talking about interpixel distance. So that finally we will come to this delta distance from the texel to the end of the pixel, what it covers. Then this is how, if this pixel, the third pixel what we are seeing, or second pixel, from the texel, if it is a distance kind of 20, then the delta distance what we are seeing, it will come as 0.6. Now if someone is a really high class mathematician, then he will compute the texel distance and pixel distance, and then so this is not the end. I am going to bring another one. Okay, so now we know that whatever the delta distance we want to kind of decrement from the texel manipulation. So now, so this delta distance would dependent upon the texel and pixel density, and this triangle length. If this is the light source, then this is light vector L, and on this surface this is the normal vector, and on the yellow surface, again red color what we see, that is the normal vector from the yellow surface. So L vector and N vector. So the angle, if it is big, the way we see on this table, then acne will be bigger, because the triangle will be longer. If triangle is longer, then interpixel length will be bigger. Okay, I can show like this. If triangle is big, then this is big. Now, if the angle is small, the way we see here, the triangle will be smaller. So pixel will be at less distance from the texel. If that is the case, then anyway we see that acne distance is less, and here it is more. So the way this angle would change from the light source of the surface, then we have to multiply tan into the r cos dot L and n. So L dot n, if I do the dot, then I receive the cos theta, and if I do the r cos, then we receive the angle, and then tan of the tangent of that angle. So whatever the delta distance we are seeing, again we have to multiply by this factor. So if angle is 0, okay, so here it is 10 to 0, then nothing is required. There should not be any acne theoretically, but there is some angle, and if angle is 0, in some situation we won't see the shadow at all. And if angle is more, the way it is growing on this surface, then tan theta will grow. Tan theta grows with the angle. Okay, if it is 90, then it is 10 to, I believe it is infinite. So the acne will be very big. So we have to take care the inferences, we have to kind of take care the pixel and texel density and the angle between the light source, the L vector, and the normal of the surface. So this much if we compute, sit back nicely, then we are done. Okay, so I'm not going to do this much. So okay, now I'm going to execute this again, and it is nearest, and this is how it is. I believe nothing has been changed. So that is the concept. So I'll have one output, and then I'll compare with researched output. Okay, so this is the beginning one. We'll leave it as a beginning one. And now what we talked. So we'll go to the shader, and here, so here I'm going to comment it. So this is C code. So comment should be different. Minus 0.001. I believe that would be okay. And now if distance from the light, okay, so if the texture distance is less than shadow code minus 001, so we are subtracting so whatever we see from the second pass, the pixel depth, that depth will decrement so that it will come on the left side. So this is what is the discussion. So shadow coordinate in the second pass, whatever z we get, we will decrement with some value so that it would be on left side. Now if it is lesser, if right side is lesser, then it will be less than distance from the light. Okay, if right side is lesser, okay, then this would be false. If distance from the light, that is the texture, is less than this, it is not less than, because it is going on the left side, it would be brighter everywhere. Okay, so we'll try now. Okay, no one stops us in time. Wow. Can we see the difference? I mean, anyone can see the difference. So, is it different? Acne is gone completely. Now we can see pleasant shadow. Okay, so I am going to move the light and it will be on the left side. Now acne is growing because the angle is decreasing. We'll do the same thing. We'll do the same thing here and we'll try our luck. Acne is there, little bit it is there. Can we see? So in the worst scenario, what we see, acne is there, but in good scenario, acne is not there. Okay, but here in good scenario also, acne is there. So we improve. This I can guarantee. If angle is less, angle is so, we are failing in this scenario. So I have to use tangent, because if kind of angle is different, then kind of this triangle, kind of its z component is different. I am not going to use that much. So okay, so I am going to increase this delta distance. So I consider this as less. So I am going to increase this. Okay, so this is how I am going to do now. Okay, so I'll make it 5. Okay, I am going to close it, Mr. Good, and I'll try again. Okay, so idea was better. Certainly it is better. Now at this angle also there is no acne, but I am not going to lose hope. There should be error. Life cannot be this easy. It's there at a very sharp angle, it is there. Can we see? Otherwise it's not there. Okay, so if someone calculates textile pixel density and tangent of the angle, then it will be completely alright, because in that fashion this hypothetical whatever we are changing now, it would change mathematically. Okay, so I can say 0.001, so I can say like 0, 0, 1, this is what we had taken initially, multiplied by 10 arc cos and then dot of ln n. Okay, and it would grow as per the scenario, but I don't want to do that much, so I'm going to increase it again. Okay, so we'll try. Okay, this would shift. If I increase, then this would shift. Okay, so that is the bottleneck. Okay, so this is transitioning acne, so it should be alright. So there is no acne. Okay, so this is how it is, and theory is theory, and practical is practical. Okay, what is the kind of next improvement that is required? We are looking at the center. We are looking at the center. Okay, we are not looking at the model. Okay, so that is the gap. Now, there is no, if I move the light source, now there is no shadow, but there should have been shadow, because light source is looking at the origin. There is no shadow, can we see? Because light source is seeing the origin, and when in that kind of frustum, GLU perspective, this is not came. Now, the one other solution is that I have to increase this angle. It is 45. If I make 60 or 70, 75, then this sphere will come into the picture, then we can see. I mean, that is a problem. I mean, it should see the sphere, not the center. So, that is the improvement that we can do. Okay, otherwise it is nice. Okay, so where are you, Mr. Sphere? Doesn't look good. Oh, it looks good. Okay, so kind of I can bind up. So we started with the shadowing in Opengl, frame buffer, arc depth buffer, texture map, shadow acne, and then adding bias. And then we see the light model, and there are two kind of camera. One is light and one is actual camera. And whatever we see from the light location, so that we can kind of through GLU look at, we can place the light at the center, and then we try to visualize how it would look. If that is the scenario, then we imagine kind of generating a texture map based upon the depth, and the raster would look like this. And then we go for actual frame buffer, and we attach a kind of a texture to the frame buffer, and in real sense we draw the raster with the depth wave. So this is what we saw. And then, so this raster is nothing but we can visualize through the images also. And then we came to conclusion that there is a texture generation phase and then actual phase. So in texture generation phase, we create the texture with the depth value, and since it is a texture, the coordinate is from 0 to 1, top right is 1 and bottom left is 0 as per the Opengl analogy of a texture. And in the final pass from the light source, again we draw the kind of with the same frustum. For each pixel we draw kind of a texel coordinate. So textile coordinate, the x and y minus 1 to 1, we kind of do add bias and then we map it here in x and y. Then z value we compare, and once we compare the z value, and then we kind of decide that it should be shadow or light, like all are light, but the area that is coming underneath the sphere, so these are coming as shadow. Okay, but we see the shadow acne because the discrete nature, digital nature of the image, where it had texels, texel density do not match with the pixel. Okay, and I do not match in a sense that they do not match physically, and this triangle, GL triangle, what we see, so GL triangle, the depth of the GL triangle left to right, this also keeps changing if we change the angle between the light and the surface normal, so that we see. So the solution we came up that for a particular texel, whatever the area it covers in the pixel, so right side should be mapped to left side so that it would be bright, and whatever average we take, texel pixel density, the ratio, in that we have to multiply the L dot n and then that angle with the tangent so that it would keep changing. If that is the scenario, then we are not getting it, 2 we get it. Okay, so shadowing was special in Opengl in the sense that we had a frame buffer, and then we kind of manipulated frame buffer in a sense that we had muted the color buffer, and then we used only the depth buffer. So that way it was different, and then whatever we drew in the frame buffer, and that we finally mapped it to the texture. So the texture pixels, it came as kind of a depth, amazing, means it is really nice. So that we saw. And what is the future now? So we have kind of seen every part in Opengl, and so future will see kind of multiple frame buffer. So whatever frame buffer we receive at the beginning, so that is not the frame buffer, that is the only we can use. So extra frame buffer we can see. So Opengl, there are image library we can see like PIL, Pillow library in Python. It also provide API to do image manipulation. So Opengl is nothing but it's a high class image manipulation libraries, and that at the end it gives us precious frames. So frame by frame we get the images. So not only the default frame buffer through which we get the frame that we see on the screen, we can have multiple frames, and then we can use them in a kind of a synchronous way, parallel or a series way, or we can do some kind of interpolation or some kind of mathematics on top of it. So that we'll see in the future, that how multiple frames, frame buffer that we can use, and then we can kind of bring realistic images, like means someone can someone is from a rope, someone is jumping from a building, and the VFX kind of the situation what we see, like two videos we merge it in a way that it means no one feels that it is not realistic. So these are kind of magic of frame buffers and the algorithms behind the scene. So those are the future. So those things we will see. And right now we are using the Opengl kind of in the transformation of the, means we are showing like universe and these kind of stuff. So slowly we will bring to realistic world, like people walking or someone is kind of driving motorbike, and then so a kind of a person can see it like a real-time life course. So that we'll see. And final idea would be like to run the frame buffers on embedded areas also. and then we can kind of merge AI kind of thing or machine learning so that it can be automated. So that is the future that we'll see in Opengl. So this is how it is.